Let's do the CSTR plus PFR series, which we've seen how to calculate the volume of a CSTR, how to calculate the volume of a PFR, how to calculate this volume of a series of PFR, which is nothing else that calculating a PFR in sections, and we've seen how or the advantages of having different CSTR reactors in series. But we are now going to mix them, which is the interesting part. In which order should you mix them in order to get the best of the arrangement? So the combination of these two types of reactors will help us to minimize the volume required to carry on a reaction to a certain conversion. So either you have 1, 2, 3 or 2, 3, 1 or 3, 1, 2. There are many arrangements you could do, but the important thing here is not to do it random, just throwing away numbers and arrangement. The important thing here is to analyze. So I got this same equation, look at this. Same rate of reaction, and you got the minimum point here, which is not that difficult to get. You can actually do it graphically, or you can do it in a software, or you can do it by doing an equation and then getting the minimum point, whatever you want, but you got the minimum. So the minimum volume, which is what we will want here, is essentially do a CSTR, because if we would have done a PFR, we will waste all these sites. But if we do a CSTR, we just get this. And that's for the left side. For the right side, if we do a, I don't know, let's say this is 90%. If we do a CSTR, will be huge. We will be wasting away all this volume. But if we do a PFR, we just take out the area under this curve or function. So this will be the minimum volume that I will expect someone to do. Now, if someone has no idea of how to do this, I normally see students throwing away random numbers and they get this. Well, as you can see, it's not good arrangement. You have a lot of volume here lost. All this volume is also extra, and this, as you can see, is extra. So if you compare with this one, actually let me transform it. Yeah, it's something like this. You got all this space thrown away. Actually, I think it's more than the double, or maybe it's only double. But here you can see how maybe it's not the maximum volume, but you get a huge amount of volume here. So what I'm trying to do with this example is to let you know that the order of the order of these reactors do matter, and this is only when it's two reactors. So imagine you will have, I don't know, 3 reactors. How will it be? And this is the case where you're designing, but what happens when you have a fixed reactor? You know, you have a specific volume and you have other type of reactor with that volume, then things come kind of messy and nonetheless very interesting. So I bring you this exercise. It is from chapter 2, Elements of Chemical Reactor Engineering, Scott Fogler, 4th edition. Example number 7, an adiabatic liquid phase isomerization of butane. So maybe you're going to tell me that this is not a reaction, and you're not right. This is a reaction. It's isomerization. You're changing from N-butane to isobutane. And they tell you this, they give you this table, which is in the next slide, and they tell you that please check out this arrangement. So that's good because they give you the arrangement. The worst thing will be that they tell you get the best arrangement, because then you will need to try CSTRs and PBRs and graph the plot of rate of reaction versus conversion, and you will need to analyze a lot. But they give you not only the arrangement but the conversions they want after each other. So you can see the first one goes from 0 to 20, the second one goes from 20 to 60, and this last one goes from 60 to 65. And they tell you to calculate it for a flow of 50 kilomoles per hour. Good, so let's do it. This is the table I told you about. The value is only minus RA, which is the rate of reaction. So that's cool, we can deal with that. rate of reaction. And okay, let's do it for 50 moles. So the first thing I want to do is to invert this data, because I know I'm going to be using this value here. And not only that, I know that I'm going to be using FA0 divided by RA. So why not do it step by step? First thing first, we invert these numbers. Secondly, we multiply by 50. And third, we put the final value here. So this is the value I will be using in the problems. I put this CSTR to remember myself that the first one goes to 20%, the second one goes from 20 to 60, and the third one goes from 60 to 65. So my tips here, which are not great deal, is calculate the volume of the continuous stir tank reactor number 1, calculate the volume of the PFR number 2, and calculate the volume of the CSTR 3. Then add all volumes and analyze why would they choose that setting. So that's optional. Actually, if I were in exam, I will do it very fast, but we are studying right now, so try to get the best of the course. Imagine, think, conceptualize, visualize, all that always help. Discuss it with your friends, with your teachers, will always be and come in handy. So the first reactor is actually is this one here, until 20%. Let's do an analysis on it. I have an inlet of 50 kilomoles. I got a conversion, which is here, and a rate of reaction, which I call check. So by definition, I got it from the formula. I got this one, B1 equals FA0, which is 50, divided by R of A. Very important that it is evaluated at the exit. The exit is 20%. So I go here. I actually want this data. I don't need this one, I don't need this one, I need this one. So 0.94, we're going to use that in here. That's my 0.94, which is here, times my conversion, which is 20 here, and I get 0.188 cubic meters. Now that's the first one, very easy. Always the first one is easy. The second one, it's not that easy, and it's a PFR, so we're probably going to do some extra calculations on the integrals. Inlet is FA1, outlet is FA2. Conversion goes from 20 to 60%, so let me do that. Volume 2 will be conversion 1, which is 20%, which is right here. Conversion 2 is 60% right here. And these values, which I got in the table right here, sorry about that, guys. I got these values here. Yeah, that's awesome. We can do it. Let's apply the trapezoid rule. My intervals will be 0.2 to 0.4 and 0.4 to 0.6, 0.2 and 0.2. That's a coincidence, but that's fine. Now let's put the range here. Let's calculate the actual heights. So I got 0.94, 0.85 and 1.3. You don't believe me? They are here, 0.94, 0.85 and 1.82. And divided by 2 to get the average, and we got this and this. But this is not what we want. We want the actual value. This will be, let's say, I'm telling you just the heights. But I don't want the heights, I want the bases, so I multiplied them. I got this base, so I got this trapezoid, and this one here. And this individual area is this area here. This individual area is this one here. Remember that it goes from 0.20 to 0.4 and to 0.6. And the addition will be, of course, the total, which is 0.397. Okay, let's keep that in mind. Look that it's almost twice, but we achieved 40%, and in the past we achieved only 20%. So that's interesting. Now, let me go back. Sorry about moving the slides that much. The final one is this here. We got 60 to 65. So probably we are expecting a very low volume, or maybe not, who knows. Okay, no, this is not the case. This one here. Inlet is FA2. Overall conversion, it's very important, guys, that this is the overall conversion, it's not the individual conversion. And the final outlet. So you could either do a mass balance, but I'm not going to do it because I already know that for every or any volume you can choose always to reference it to the initial one. And since I know the global conversions, that's cool, because if I didn't know this was global, if it were, let's say, a single pass, I wouldn't be able to do this, and I will have to do it step by step, which will be and take me a lot of time. But in this case, I know it's global, so I can do and apply this formula. Very important though, we still need to apply it for the 65%. Okay, so F of A divided by the rate of reaction at 65%. Let me check it out. It's right here. I don't need this, I don't need this, I want these two. So let's go here. And you know that this guy right here is 2. So let me set it up here, times the difference of conversion, which makes sense, and actually will be only 5% or 0.05, times 2, which is 0.1. The volume is 0.1. So let's rearrange our system. This was 1, this one 2, and this was 3. B1, B2, B3. I got 0.18, 0.39, and 0.1. If I add up all these, I got 0.68 cubic meters. So that's interesting. That's the value I got, and actually I think it's the same one in the book. So that was how we mix CSTRs and PFRs. Of course, there are more problems we could do. We could, as I told you before, let you free and to choose which arrangement which you choose to maximize conversion and minimize volume. Or we could also make you not give you the overall conversions, but the single conversions. That will make it a little bit more difficult to, well, not difficult, but larger procedures, mathematical calculations, and so on. So you want to check more about that, go to this web page, go to the courses, to Reactor Engineering. I got a lot of solved problems there. They will help you to get the best of the course, because you know theory, you can find this in the book, I just explained it. But if you want to really get better, or you want to be the best, you need to check out more problems. And yep, just go to chapter 2 and you will find them already solved for you. And it's time to enter section number 4, which is the last one of the block. What's up guys, it's me, Chemical Engineering Guy. So if you like the video, why not push the like button? It really helps me to know if you're liking the videos, or if I should be changing something, or I should be adding something, taking out content, whatever. Also, sharing is caring. So if you got any kind of friends, teachers, colleagues, or whatever kind of person that might be interested in this type of content, why not share it? Sharing helps our community to grow faster in members and in content. If you want to keep track of my activity, videos, uploads, experiments, playlists, whatever content I'm getting on YouTube, be sure to click the subscribe button. Subscribing to the channel is totally free, guys. My dream is to create an online academy of chemical engineering, where everyone can access it in the world. Imagine a place in which the student, the teacher, and the engineer get the best of each other. Thank you guys for the support and the love.